Cold fusion. On March 23, 1989, electrochemists Stanley Ponce and Martin Fleischmann held a press conference at the University of Utah that shocked the scientific world. They announced they had achieved nuclear fusion at room temperature using a simple tabletop apparatus. If true, it would solve the world's energy problems overnight. Unlimited clean power generated in a beaker of water. The announcement was extraordinary. Nuclear fusion, the process that powers the sun, requires temperatures of millions of degrees and massive containment facilities. The idea that it could happen in a jar on a laboratory bench seemed impossible. Yet, Ponce and Fleischmann, both respected electrochemists, claimed they had measured excess heat and detected fusion byproducts in their experiments. The university held the press conference before the research was peer-reviewed or published, an unusual break from scientific protocol. University administrators were aware of the massive commercial implications and wanted to establish priority for the discovery. Patent applications were filed. The media coverage was enormous. Fusion in a jar became headline news worldwide. Within days, laboratories around the world were attempting to replicate the experiment. The apparatus was simple: a palladium electrode in heavy water, deuterium oxide, with an electric current running through it. Ponce and Fleischmann claimed the palladium absorbed deuterium atoms so densely that fusion occurred, releasing energy. Some labs reported positive results, detecting excess heat, but most could not replicate the findings. More importantly, the experiments lacked the telltale signs of fusion, specifically the neutron radiation that fusion reactions produce. The heat Ponce and Fleischmann detected wasn't accompanied by the nuclear byproducts that should have been there. By May 1989, the American Physical Society held a special session on cold fusion. Physicist Stephen Koonin presented a devastating analysis showing that the claimed fusion rates were incompatible with the observed neutron production. The scientific consensus turned sharply against cold fusion. It was declared a mistake at best, fraud at worst. The University of Utah, which had initially supported the research with funding and publicity, began distancing itself from the claims. By 1991, the university's National Cold Fusion Institute closed. Ponce and Fleischmann left the United States. Ponce resigned from the university, and both scientists relocated to France, where they continued research funded by Toyota. But here's where it gets interesting. The official denial of cold fusion may have been premature. In subsequent decades, experiments under the label low-energy nuclear reactions, LENR, have continued to show anomalous heat production that conventional chemistry cannot explain. The U.S. Navy's research lab has published papers documenting excess heat in similar experiments. NASA has investigated LENR as a possible power source for spacecraft. In 2015, a major Japanese company demonstrated a nickel-hydrogen reaction system that produced significant excess heat. Several startups and research groups continue to work on variations of the original cold fusion concept. The phenomenon Ponce and Fleischmann observed may have been real, but not the deuterium-deuterium fusion they claimed. The discovery was announced with great fanfare, officially denied and ridiculed by mainstream science, yet research quietly continues. Whether cold fusion was an error or a suppressed breakthrough remains one of science's most controversial questions. Arsenic-Based Life. On December 2, 2010, NASA held a press conference that promised to announce a discovery that would impact the search for evidence of extraterrestrial life. The announcement generated massive speculation. Had NASA found alien life? The actual announcement was almost as shocking. NASA astrobiologist Felisa Wolf-Simon and her team claimed they had discovered a bacterium that could incorporate arsenic into its DNA in place of phosphorus. This was revolutionary because all known life on Earth uses 6 essential elements, including phosphorus, in its genetic material. A bacterium that substituted arsenic would represent a fundamentally different form of life. A second genesis, showing that life could evolve using different chemical building blocks. The bacterium, designated GFAJ1, was isolated from Mono Lake in California, an environment with high arsenic concentrations. When the researchers grew the bacteria in an environment with arsenic but no phosphorus, the bacteria survived and appeared to incorporate arsenic into their biomolecules. The implications were profound. If life could use arsenic instead of phosphorus, it suggested that alien life might be far more diverse and resilient than we imagined. The search for extraterrestrial life could expand to environments previously thought uninhabitable. The research was published in the prestigious journal Science. NASA's public relations machine went into high gear. Media coverage was enormous. Scientists around the world discussed the implications for astrobiology and the search for alien life. Then the scientific community began scrutinizing the research closely. Within days, serious questions emerged. Critics pointed out that the paper's evidence for arsenic in DNA was circumstantial. The researchers hadn't actually proven that arsenic was chemically bonded into the DNA backbone. They had only shown that arsenic was present in the cells. Several research groups attempted to replicate the findings. They found that GFAJ1 bacteria survived in arsenic-rich, phosphorus-poor environments, not by replacing phosphorus with arsenic, but by scavenging tiny amounts of residual phosphorus from the growth medium. The bacteria were extremely efficient at extracting phosphorus, not revolutionary in their biochemistry. In 2012, two separate research teams published papers in Science showing that GFAJ1 bacteria could not actually incorporate arsenic into their DNA. They demonstrated that the bacteria required phosphorus to grow and used standard biochemistry, not the exotic arsenic-based system NASA had announced. NASA quietly backed away from the discovery. The agency's website was updated with language emphasizing that the work was ongoing and under review. Wolf Simon, who had been celebrated as a pioneering astrobiologist, faced intense criticism and scrutiny. By 2013, the scientific consensus was clear. Arsenic-based life had not been discovered. GFAJ1 was an interesting extremophile bacteria adapted to high arsenic environments, but it used conventional biochemistry. The revolutionary discovery that NASA had announced to the world was officially denied. What went wrong? Critics accused NASA of prioritizing publicity over proper scientific vetting. The press conference occurred before the scientific community had thoroughly evaluated the research. The desire for a sensational announcement led to claims that weren't supported by the evidence. The arsenic-based life announcement and subsequent retraction became a cautionary tale about science by press conference and the dangers of overhyping preliminary findings. Faster-than-light neutrinos. On September 23, 2011, physicists working on the Opera experiment at the Gran Sasso Laboratory in Italy made a stunning announcement. They had detected neutrinos traveling faster than the speed of light. If confirmed, this would overturn Einstein's theory of relativity, the foundation of modern physics. The experiment measured neutrinos generated at Schön in Switzerland and detected them at Gran Sasso in Italy, 730 kilometers away. According to their measurements, the neutrinos arrived 60 nanoseconds earlier than light would have traveled the same distance. The particles were exceeding light speed by about 0.025%. The Opera collaboration consisted of over 160 scientists from 30 institutions. Before making the announcement, they spent months checking and rechecking their data. They examined every possible source of error they could imagine. Finding none, they published their results and held a press conference, carefully noting that the findings were preliminary and needed independent verification. The announcement caused a sensation. Physicists around the world debated what it could mean. Some suggested new physics beyond relativity. Others proposed exotic explanations involving extra dimensions or quantum effects. Most were skeptical, but intrigued. The scientific community mobilized to verify the results. Other neutrino experiments began examining their own data for similar effects. Theorists wrote papers exploring the implications. If neutrinos really traveled faster than light, it would be the biggest physics discovery in a century. Then, in February 2012, just 5 months after the announcement, the Opera collaboration made a new statement. They had found two potential sources of error in their experiment. One was a loose fiber optic cable in the timing system. The other was a faulty oscillator used to timestamp the neutrino detections. When these errors were corrected, the faster-than-light effect disappeared. The neutrinos traveled at exactly the speed they should, just under the speed of light, consistent with Einstein's theory. The discovery was officially retracted. the opera collaboration published a new paper acknowledging the error. The experiment's spokesperson, Antonio Ereditado, and physics coordinator, Dario Autiero, resigned their positions. Other experiments, Icarus at Gran Sasso and Borexino, confirmed that neutrinos travel at light speed, not faster. The revolutionary discovery that had briefly challenged Einstein was gone. What makes this case interesting is how it was handled. The opera team announced preliminary results specifically requesting verification, acknowledged their error openly, and retracted the claim as soon as the mistakes were found. This is science working as it should, but it still resulted in a discovery announced and then denied. The faster-than-light neutrino incident highlighted the challenges of cutting-edge experimental physics, where measurements are at the edge of technical capability, and tiny errors can produce extraordinary false results. The face on Mars. In July 1976, NASA's Viking 1 orbiter photographed the Cydonia region of Mars. Among the images was one that appeared to show a massive face carved into the Martian surface, a humanoid face nearly 2 miles long, staring up at the sky. NASA released the image with a caption describing it as a face-like mesa, and noting that it was a trick of light and shadow. But the public imagination was captured. The face on Mars became one of the most famous images in space exploration history. By the 1980s, researchers examining the Viking images more closely claimed the face was part of a larger complex of artificial structures. Richard Hoagland, a former NASA consultant, published extensive analysis arguing that the face was accompanied by pyramid-like structures and what appeared to be a city complex. He claimed these were built by an ancient Martian civilization. Books were written, documentaries were produced. The face on Mars became embedded in popular culture as potential evidence of extraterrestrial intelligence. Some researchers claim to have found mathematical relationships between the structures, suggesting deliberate design. NASA maintained that the face was a natural mesa, but the agency's denials only fueled speculation. Critics accused NASA of suppressing evidence of alien civilization. The agency was caught in an awkward position. The more they denied the face's significance, the more conspiracy-minded people suspected a cover-up. The controversy reached such proportions that, when NASA planned the Mars Global Surveyor mission in the 1990s, they specifically promised to re-photograph the face with better cameras. This was unusual, an entire space agency adjusting its mission priorities to address what they insisted was simply a curious rock formation. In April 1998, Mars Global Surveyor photographed the Cydonia region with cameras 10 times more powerful than Viking's. The new images showed the face in much higher resolution. The result was unambiguous. It was a natural mesa. The face-like appearance in the Viking image was indeed a trick of light and shadow, combined with low resolution. The eyes were impact craters. The mouth was just an irregular rock formation. Seen from different angles and with better lighting, the formation didn't look like a face at all, just an eroded butte like thousands of others on Mars. NASA had finally proven what they had claimed all along. The face on Mars was natural geology, not artificial construction. The discovery of an alien monument had been officially denied. But believers weren't convinced. Some claimed NASA had altered the new images. Others argued that the face had been deliberately destroyed between the Viking and Global Surveyor missions. Hoagland and others continued to insist that analysis of the structures showed artificial geometry. The face on Mars represents a discovery that NASA never actually announced. The public and independent researchers made the claim. NASA spent decades denying it, then finally produced evidence proving their denial. Yet for many, the face remains evidence of ancient Martian civilization, regardless of what better photographs show. Room temperature superconductor. In July 2020, physicist Ranga Dias of the University of Rochester announced a breakthrough. His team had created a material that exhibited superconductivity at room temperature under high pressure. The research was published in the prestigious journal Nature. If confirmed, it would be one of the most important physics discoveries of the century. Superconductors, materials that conduct electricity with zero resistance, have enormous potential applications, from ultra-efficient power grids to levitating trains to quantum computers. But known superconductors only work at extremely cold temperatures, making them impractical for most uses. A room temperature superconductor would revolutionize technology. Dias's material was a carbonaceous sulfur hydride subjected to extreme pressure, about 267 gigapascals, roughly 75% of the pressure at Earth's core. Under these conditions, the material showed the hallmark signs of superconductivity at temperatures up to 15 degrees, 59 degrees, the first time superconductivity had been achieved above freezing. The announcement generated enormous excitement in the physics community. Here was experimental evidence of a phenomenon that had been theorized but never achieved. Multiple news outlets covered the discovery. Dias became a scientific celebrity. But questions quickly emerged. Other research groups noted unusual features in the published data. Some graphs appeared to have been manipulated or processed in ways that weren't fully explained. Researchers requested the raw data to verify the findings, but Dias declined to share it, citing competitive concerns and intellectual property. By 2022, the journal Nature was investigating the paper. Multiple physicists had submitted formal complaints about the data. Some pointed out that certain measurements looked suspiciously smooth, lacking the noise and variation expected in experimental data. In September 2022, Nature took the extraordinary step of retracting the paper. The retraction notice stated that the editors had lost confidence in the reliability of the published data. Dias disputed the retraction, insisting his results were valid, but the story didn't end there. In March 2023, Dias published a new paper in the same journal, Nature, claiming another room temperature superconductor using a different material, nitrogen-doped lutetium hydride. This material allegedly exhibited superconductivity at 20 degrees under lower pressure. The announcement was met with immediate skepticism, given the previous retraction. Multiple labs attempted to replicate the findings. Most failed. Again, questions arose about data manipulation in the paper. By August 2023, this second paper was also retracted by Nature, again citing concerns about data reliability. The University of Rochester launched an investigation into Dias's research practices. Here was a discovery announced not once but twice in prestigious journals, only to be retracted and officially denied both times. Whether Dias observed genuine phenomena that he misinterpreted or engaged in deliberate fraud remains under investigation. But the room temperature superconductor discovery has been officially retracted, twice. Water canals on Mars. In 1877, Italian astronomer Giovanni Schiaparelli published observations of Mars using a large telescope. He reported seeing long, straight lines crisscrossing the Martian surface, which he called canali, Italian for channels. The word was mistranslated into English as canals, implying artificial construction. American astronomer Percival Lowell seized on this discovery. From his observatory in Flagstaff, Arizona, Lowell observed Mars extensively and claimed to see hundreds of canals forming a vast network across the planet. He published maps showing elaborate canal systems and argued they were constructed by an intelligent Martian civilization to transport water from the polar ice caps to the equatorial regions. Lowell's books and lectures popularized the idea of Martian canals. He argued that Mars was a dying world, becoming increasingly arid, and that the Martians had built the canals as a desperate effort to survive. His vivid descriptions captured public imagination and inspired science fiction, including H.G. Wells's The War of the Worlds. The Martian canals became accepted as fact by much of the public and even some astronomers. Lowell was a respected scientist, and his detailed maps and observations seemed convincing. The discovery of an extraterrestrial civilization was officially announced and widely believed. But many astronomers were skeptical. When they looked at Mars through their telescopes, they saw a blurry reddish disk with some darker patches, but no clear straight lines. British astronomer Edward Maunder suggested the canals were an optical illusion, the human eye's tendency to connect random features into linear patterns when viewing fine details at the edge of visibility. As telescopes improved and photographic techniques advanced, the canals became harder to see, not easier. If they were real features, better observations should have made them more distinct. Instead, they seemed to fade away as observation quality improved. The final denial came when spacecraft visited Mars. Mariner 4 flew by in 1965 and sent back the first close-up images of Mars, no canals. Mariner 9 orbited Mars in 1971 and mapped the entire planet. Again, no canals. The Viking orbiters in 1976 photographed Mars in extraordinary detail. The planet's surface showed impact craters, volcanoes, canyons, and dry riverbeds from ancient water flow, but no straight canals. The Martian canals didn't exist. They had never existed. Lowell and others had seen an optical illusion, a trick of human perception when viewing fine details through atmospheric turbulence and with instruments at the limit of their resolution. The discovery of a Martian civilization, announced and defended for decades, was officially denied by photographic evidence. The canals weren't suppressed or covered up. They simply weren't there. What makes this case fascinating is how a respected scientist could announce a discovery, create detailed maps of non-existent features, and defend his observations for years. It demonstrates how observer bias and the limitations of technology can create discoveries that later observations deny. Polywater. In the early 1960s, Soviet scientist Nikolai Fedyakin announced a discovery that puzzled and excited chemists worldwide: a new form of water with radically different properties from normal H2O. This anomalous water had a higher boiling point, lower freezing point, higher viscosity, and different density than ordinary water. The discovery was initially dismissed by Western scientists, but when Boris Derjagin, a prominent Soviet physical chemist, confirmed Fedyakin's findings and presented them at international conferences, the scientific community took notice. Derjagin suggested the water molecules were arranging themselves in a unique polymerized structure, polywater. By the late 1960s, laboratories around the world were attempting to replicate the Russian findings. Some succeeded, creating small amounts of this strange liquid in glass capillary tubes. The substance did indeed show unusual properties. Scientific papers proliferated. Media coverage increased. Polywater became a hot topic in chemistry. The implications seemed profound. If water could exist in a new stable form, it might have applications in industry and biology. But there was also concern. Some scientists worried that if polywater was more stable than regular water, it could catalyze the conversion of Earth's oceans into polywater, turning the planet into a lifeless desert. This apocalyptic scenario was mostly speculation, but it captured public imagination. At the height of polywater research, hundreds of papers were published about this new form of water. Major laboratories dedicated resources to studying it. The U.S. government funded polywater research, concerned about falling behind the Soviets in what appeared to be an important discovery. Then doubts emerged. Chemists noticed that polywater samples contained impurities, bits of silicon from glass tubes, organic compounds from handling, salt from sweat. When extremely careful purification was attempted, the anomalous properties disappeared. In 1971, physicist Denis Rousseau published a paper showing that polywater was simply water contaminated with silica and other impurities. The unusual properties weren't from a new water structure, but from dissolved contaminants. Multiple research groups confirmed this finding. Derjagin, the primary champion of polywater, eventually accepted the evidence. In 1973, he published a paper acknowledging that polywater was a mistake. The observations were of contaminated water, not a new molecular structure. The discovery was officially retracted. Polywater didn't exist. The hundreds of scientific papers, the government funding, the international conferences, all had been devoted to studying an artifact of impure laboratory conditions. The polywater episode became a classic case study in pathological science, how a combination of experimental error, observer bias, and the desire for a dramatic discovery can lead the scientific community astray. The discovery was announced, investigated worldwide, and then definitively denied when better experiments showed it was an illusion. Schön's superconducting breakthroughs. Between 1998 and 2001, physicist John Hendrik Schön, working at Bell Labs, published a series of papers announcing breakthrough after breakthrough in condensed matter physics. He reported achieving superconductivity in novel materials, creating organic transistors that worked at the molecular level, and discovering quantum effects in simple systems. His productivity was astonishing. At his peak, he was publishing a major discovery every 8 days. Schön's papers appeared in the most prestigious journals: Science, Nature, Physical Review letters. He claimed to have created the first organic superconductor, the first molecular-scale transistor, and achieved superconductivity in materials thought impossible. Each discovery would have been worthy of major scientific recognition. Together, they seemed to herald a revolution in electronics and materials science. The physics community celebrated Schön as a rising star. He received multiple prestigious awards. His work was cited extensively. Bell Labs promoted his research aggressively. Some speculated he was on track for a Nobel Prize. But as more physicists tried to replicate his results, problems emerged. No one could reproduce his findings. Schön attributed this to the extreme difficulty of his experimental techniques, which he claimed required extraordinarily precise conditions. In 2002, several physicists noticed something disturbing. Different experiments in Schön's papers showed identical noise in the data graphs. This was statistically impossible. Random experimental noise should never be identical across separate experiments. It suggested the data wasn't real measurements, but fabricated numbers. Bell Labs launched an investigation. They assembled a committee of independent scientists to examine Schön's work. The committee's findings, released in September 2002, were devastating. Schön had engaged in systematic scientific fraud. He had fabricated data, falsified experiments, and in some cases, simply invented numbers to create the results he wanted. At least 16 of his papers were found to contain fraudulent data. The discoveries he had announced, the organic superconductors, the molecular transistors, the breakthrough quantum effects, didn't exist. None of them had been real. The journals began retracting Schön's papers en masse. Ultimately, 28 papers were officially retracted, one of the largest scientific fraud cases in history. Schön was fired from Bell Labs. His PhD was revoked by the University of Konstanz. Co-authors who had trusted his data had their reputations tarnished. The discoveries that had promised to revolutionize electronics were officially denied. They had never been real. Schön had fabricated them all. What made Schön's fraud particularly effective was that his claimed discoveries were plausible. They were things physicists thought might be possible. He published in fields where verification was difficult and experiments were complex. And he exploited the competitive pressure to publish quickly in prestigious journals, which sometimes led to inadequate peer review. The Schön scandal led to major reforms in how scientific results are verified and how journals handle data. But it remains a stark reminder that even the most prestigious announcements can be denied when careful investigation reveals fraud. N-rays. In 1903, French physicist René Blondelot, a member of the French Academy of Sciences, announced the discovery of a new form of radiation he called N-rays, after Nancy, his home city. This came just 8 years after Röntgen's discovery of X-rays, at a time when new forms of radiation were being found regularly. Blondelot claimed N-rays were emitted by many substances, including the human nervous system. They could pass through aluminum, but not wood or water. They could be refracted by certain materials and focused by aluminum lenses. Most intriguingly, N-rays slightly increased the brightness of phosphorescent materials and made small sparks appear brighter, allowing them to be detected by trained observers. The discovery was announced in France's most prestigious scientific journals. Within months, dozens of French scientists confirmed Blondelot's findings. They published papers detecting N-rays from various sources and documenting their properties. French physics was celebrating a major national scientific triumph. But scientists outside France, particularly in Britain and Germany, couldn't replicate the findings. When they attempted to detect N-rays using Blondelot's methods, they saw nothing. The effects seemed to work only for French researchers. American physicist Robert W. Wood decided to investigate. He visited Blondelot's laboratory in 1904 to observe a demonstration. Blondelot showed how N-rays passing through an aluminum prism could be detected by their effect on a phosphorescent screen. The experimenter, working in near darkness, reported seeing changes in the screen's brightness. Wood conducted a simple test. When Blondelot wasn't looking, Wood secretly removed the aluminum prism from the apparatus. The experiment continued, and the experimenter continued reporting the effects of N-rays being refracted by the prism, which was no longer there. The observations were based entirely on expectation, not reality. Wood published his findings, exposing N-rays as an illusion. The radiation didn't exist. The French scientists had been seeing what they expected to see in dark rooms, watching for tiny changes in brightness that were actually just random variations in their own visual perception. The revelation was devastating for French physics. The Academy of Sciences stopped publishing N-ray papers. Blondlot himself never accepted that N-rays were illusory and defended his discovery until his death, but the scientific community officially denied the discovery. Over 300 scientific papers had been published about N-rays by French researchers. All were retracted or dismissed. The discovery was a case of pathological science driven by observer bias, where researchers saw what they expected to see because the detection method relied on subjective perception rather than objective measurement. N-rays became a cautionary tale about the importance of independent verification and objective measurement in science. The discovery was announced with great confidence, confirmed by dozens of researchers, and then officially denied when proper investigation showed it was an illusion. Piltdown Man. In 1912, amateur archaeologist Charles Dawson announced an extraordinary discovery. He had found fragments of a skull in a gravel pit near Piltdown, England, that appeared to be the missing link between apes and humans. The skull had a human-like cranium, but an ape-like jaw, exactly what evolutionary theory predicted the transitional species should look like. The discovery was presented to the Geological Society of London and examined by leading British paleontologists. Arthur Smith Woodward of the British Museum authenticated the find. The specimen was named Eoanthropus dawsoni, Dawson's Dawn Man, and declared to be 500,000 years old. Piltdown Man became the pride of British paleontology. It proved that modern humans had evolved in England, not Africa, as some suspected. The discovery was featured in textbooks, museums, and scientific papers. Plaster casts of the skull were sent to museums worldwide. Scientists built evolutionary theories around Piltdown Man's unique combination of features. But as more hominin fossils were discovered elsewhere, Piltdown Man became increasingly anomalous. Fossils from Africa and Asia showed a different pattern, ape-like skulls with human-like teeth, the opposite of Piltdown. By the 1940s, Piltdown Man seemed to contradict every other human fossil ever found. In 1953, British Museum scientists Kenneth Oakley, Wilfrid Le Gros Clark, and Joseph Weiner applied modern dating techniques to the Piltdown fossils. The results were shocking. The skull was indeed ancient, about 600 years old, but the jaw was modern, from an orangutan that had died recently. The teeth had been filed down to look human. The bones had been stained with chemicals to appear old. Piltdown Man was a hoax. Someone had deliberately created a fake fossil by combining a human skull fragment with an orangutan jaw, modifying them to look like a transitional species, and planting them in the gravel pit. The discovery that had shaped British paleontology for 40 years was officially denied. Museums removed Piltdown Man from displays. Textbooks were rewritten. Scientific papers built on Piltdown evidence were invalidated. Who created the hoax remains uncertain. Dawson is the primary suspect, but some researchers believe others were involved. What's clear is that the scientific establishment accepted the find because it confirmed what they wanted to believe, that humans had evolved in England and that the first evolutionary step was developing a large brain. Piltdown Man represents not just a discovery announced and then denied, but a deliberate fraud that fooled the scientific establishment for decades. The denial came only when better dating techniques proved the fossil was fake. These 10 cases represent some of the most significant retractions in scientific history. Discoveries that were announced with confidence, often in prestigious journals and with the backing of major institutions, were later officially denied when evidence showed they were wrong, misinterpreted, or in some cases, deliberately fabricated. What unites these cases is not the simple fact that scientists made mistakes. That's part of science. What's remarkable is how far these discoveries progressed before being retracted. Cold fusion was announced at a major press conference. Arsenic-Based Life was promoted by NASA. room temperature superconductors were published in Nature, twice. These weren't preliminary findings quietly discussed in labs. They were major announcements that shaped public understanding and scientific research. Some retractions came from honest error. The faster-than-light neutrinos resulted from a loose cable, and polywater from contaminated samples. Others resulted from insufficient verification, like the arsenic-based bacteria, where the initial results were overhyped before careful checking. And some were deliberate fraud, like Schön's fabricated breakthroughs and the Piltdown hoax. The scientific method is designed to be self-correcting. Discoveries must be verified through replication and peer review. When findings can't be replicated, or when better evidence contradicts initial results, science must be willing to retract and deny even its most celebrated announcements. But these retractions raise uncomfortable questions about how discoveries are announced in the first place. The pressure to publish in prestigious journals, the competition for funding and recognition, the desire for media attention, all can push scientists to announce findings before they're fully verified. And once announced, especially with institutional backing and media coverage, retracting becomes professionally devastating. The discoveries in this video were announced, celebrated, built upon, and then denied. Whether through honest error, inadequate verification, or deliberate deception, they remind us that even scientific announcements from respected institutions can be wrong. The difference between a discovery and a retraction sometimes lies not in the quality of the initial research, but in the willingness to check it carefully before announcing it to the world.